Hello, I'm SeungJeh Chung from III Excel Lab. Today I'll be talking about text-to-3D generation. Especially, I'll focus on the well-known method score distillation sampling, which is also called SDS, and the improved method interval score matching, which is called ISM. This presentation is based on the LucidDreamer paper published at CVPR 2024, and I've prepared it in a way that's easy to follow. Now, one of the most exciting advancements in AI recently is in the field of generative AI. For example, tools like Midjourney and DALL-E have achieved remarkable performance and even reached commercial success. These technologies are designed to automatically create images based on text prompts provided by users. We call this type of task text-to-2D generation. This text-to-2D generation has been researched so extensively that it can now produce results of commercial quality. And for next step, in the past year, the focus has expanded from 2D to generating even more complex 3D outputs. For example, if you input a text like a penguin or a cactus plant, it's no longer just about creating a 2D image. Now it's possible to generate 3D models like meshes or point clouds. So, as shown in the bottom image, you can even create something like a 3D model of a fox from a text prompt. And that brings us to today's topic, text-to-3D generation. First, let me explain the basic pipeline of text-to-3D generation. Of course, it all starts with a text prompt. For example, let's say you input something like a DSLR photo of a sitting cat wearing a VR headset. Based on that text prompt, the system generates a 3D representation. There are various types of 3D representations such as mesh, point cloud, NURF, and 3D Gaussian. By defining values for geometry and color, you can shape the appearance to match what you want. So, to make the 3D representation match the appearance described, described by the text prompt, you need to train the parameters of the elements or functions that define geometry and color. The goal here isn't to reconstruct something that already exists in reality. Instead, it's about creating entirely new, imaginative 3D models like a cat wearing a VR headset based purely on text. But text and 3D representations are completely different types of data. How can we train a AI model to generate 3D representations from text? AI model relies heavily on large amounts of data for training, but when it comes to 3D representation, creating datasets or collecting data using equipment is challenging and time-consuming task. As a result, there aren't many large datasets or well-trained AI models for 3D. On the other hand, 2D images are abundant and there are already AI models trained on massive data with excellent performance. For example, models like clip or diffusion models have been trained on huge paired datasets of text and images, enabling them to generate text and images interchangeably. Using these 2D vision and language pair pre-trained models to train 3D representations is what we call the lifting 2D to 3D technique. In this approach, the 3D representation is rendered into 2D images and then input into a pre-trained vision language model along with the text prompt. The most well-known model for this is the diffusion model. A well-trained diffusion model can infer 2D visual information that matches the meaning of the text. By repeatedly backpropagating this inferred prior to update the learnable parameters of the 3D representation, you can eventually train it to capture the appearance described by the text. Additionally, since the 3D representation is trained using 2D information, relying on images rendered from just one view means that other perspectives won't be learned. To address this, rendered multiple images from different views helps capture the full 3D structure and prevents the loss of information that can occur when projecting 3D into 2D. Going back to the key point, what really matters is how the diffusion model learns the text to 2D image generation. Think of a diffusion model like dropping ink into water. It's an easy way to understand the concept of diffusion. When you drop ink into water, it gradually spreads out over time until it looks completely diffused, like a blob of color. To reverse this process, you'd need to predict how the ink spread and then sequentially remove the diffusion step by step. In the same way, a diffusion model adds Gaussian noise to an image step by step until it turns into pure noise. The goal is to reverse this process by predicting the noise added at each time step and removing it sequentially to recover the original image. The DDPM, which stands for Denoising Diffusion Probabilistic Model, is a probabilistic generative model that progressively adds noise to data and removes it to reconstruct or generate images. In this video, instead of diving into the probabilistic definitions or equations, I'll focus on explaining the key steps and formulas that show how the diffusion model actually works. The first step in a diffusion model is the forward diffusion process, where noise is gradually added to the original image x0 to transform it into a noisy latent representation xt. Gaussian random noise Gaussian random noise epsilon t is sampled from a Gaussian distribution at each time step t, and noise is gradually added from step 0 to step t. The process of adding noise at each time step can be defined based on a fixed scheduling weight, which can be expressed with the following equation. One thing to keep in mind is that if you combine all the noise epsilon t added across the time steps, it can be represented as a single cumulative noise epsilon. This becomes one of the key features in the noising process of SDS. I'll explain more about it in the upcoming slides. The second step of the diffusion model is the reverse denoising process, where the goal is to remove the noise from the noisy latent xt to recover the original image x0. To do this, the model predicts the noise that was added at each time step during the forward process and removes it step by step. This task of predicting the noise epsilon is handled by a neural network. This task of predicting the noise epsilon is handled by a neural network like UNet. When the noisy latent xt is passed through the UNet, it outputs epsilon pi, which is the predicted noise that is expected to have accumulated up to time step t. The unit is trained to ensure the predicted noise epsilon phi coverage to the actual edit noise epsilon. So by training the unit to minimize the difference between epsilon and epsilon phi, it learns to predict noise that closely matches the actual noise added. By removing this predicted noise step by step from noise latent xt, the model can reconstruct the original image. In the end, the loss function for the diffusion model can be formulated as the L2 loss between epsilon and epsilon phi. This loss incorporates the mean of the noise added at t. At this point, you might wonder how the text prompt actually gets included in this training process. To include the text prompt in the training, the text describing the original image is embedded using a neural network like CLIP. Then, this embedding is provided as a condition to the unit. In this setup, the noise predicted by unit is trained to align with both the image and the text information. You just need to add the text condition y to the noise equation in unit. Once the diffusion model is trained on a large vision and language pair dataset, it can generate 2D images from text prompts. The denoising process acts as the generation pipeline. By providing the noisy latent and the text prompt as inputs, the unit predicts epsilon phi. Gradually removing this predicts noise step by step until time step 0 results in a text-guided image. Going back to the text-to-3D pipeline, the technique used to train 3D representation based on the pre-trained diffusion model is called SDS. The SDS, which stands for Score Distillation Sampling, treats the noise predicted by a diffusion model as a score that shows how far the current result is from the target. This score is used to guide the process of updating the 3D representation until it aligns closely with the desired text prompt. The pre-trained diffusion model takes a noisy latent and a text prompt as inputs, so noise needs to be added to a 2D image to create a noisy latent before feeding it into the diffusion model. In other words, the image rendered from the 3D representation goes through a noising process first. The noising process in SDS is different from the forward process that gradually adds noise to an image over time steps. Due to the properties of linear combination of Gaussians, multi-step noising can be replaced with one-step noising. As explained earlier, Gaussian noise can be combined using a scheduling weight to represent cumulative noise epsilon. This means adding a single Gaussian noise to an image can be treated as adding the cumulative noise from multiple steps. So the noisy latent xt at time step t can be quickly and easily computed by adding noise epsilon to the original image x0 in just one step, making the process much faster and simpler. To summarize the entire process in equations, the learnable 3D representation theta is passed through the rendered function g, producing a 2D image x0. Then Gaussian noise epsilon linearly combined with x0 based on scheduling weight, resulting in the noisy latent xt. So noisy latent xt and text prompt y are input into the unit, which predicts epsilon phi, the estimated noise. The objective of SDS is to compare epsilon phi with the added noise epsilon from the noising process. The comparison is formulated as the SDS loss, which is an L2 loss. By backpropagating the SDS loss as a diffusion prior and updating the 3D representation's parameters zeta, the 3D representation progressively learns the visual information described by the text prompt. Over time, this process generates the geometry and color to match the desired vision. Let's simplify this with a more intuitive equation. The SDS loss can also be interpreted as the difference between images instead of difference between noise values. By rearranging the existing equations without introducing any additional terms, the SDS loss can be expressed as the L2 loss between the rendered image x0 and the denoised image x hat, where x hat is obtained by removing the predicted noise epsilon phi from the noisy latent xt. This is represented by the equation shown in blue, highlighting the relationship between the rendered image and the denoised image. In other words, the 3D representation is rendered into a 2D image, then passed through a noising process to create a noisy latent. This noisy latent, along with the text prompt, is input into the diffusion model. From there, the unit predicts the noise which is used to denoise and produce denoised images. Revisiting this in terms of equations, it can be illustrated with the following figure. Rendered image x0 is noised and denoised by text-conditioned diffusion, producing text-conditioned denoised image x hat. Since denoised image x hat is generated based on the desired text prompt, it can be defined as pseudo ground truth for training text-based 3D representation zeta. In summary, SDS loss train 3D representation zeta by minimizing the difference between rendered image x0 and text-conditioned pseudo-GT x hat for text-to-3D generation. But SDS has two major limitations. First, the Gaussian random noise added to the rendered image creates a stochastically varying pseudo-ground truth. This stochastic variation leads to over-smoothed results because of the averaging effect. Second, diffusion models are trained with a progressive noising and denoising process across time steps. However, in the SDS formulation, the pseudo-ground truth is generated by adding and removing cumulative noise in a single step. This approach can lead to low-quality guidance, especially at large time steps. In other words, as shown in this figure, the over-smoothing of pseudo-GT caused by averaging random sampled noises and the low quality of pseudo-GT generated through one-step noising and denoising can ultimately degrade the final generation performance. To overcome the limitations of low-quality guidance and over-smooth research in SDS, a method called DDIM inversion, which stands for Denoising Diffusion Implicit Models inversion, was proposed. Building on this, the ISM, which stands for Interval Score Matching, approach was developed. The first paper to propose these techniques for text-to-3D generation is LucidDreamer. The image below shows the results of 3D objects generated from text prompts using LucidDreamer. In my opinion, it represents the most advanced outcomes among the current text-to-3D generation methods. The noising process in SDS is performed in a single step using cumulative random noise, that is stochastic noise. On the other hand, DDIM inversion defines an interval step delta between time step 0 and t. At each step, the noise predicted by the unit is repeatedly added and removed, creating an invertible trajectory for the noisy latent. By calculating this noisy latent trajectory, deterministic noise can be added to and removed from the rendered image over multiple time steps. The ultimate goal of DDIM inversion is to add noise to the rendered image to create a noisy latent. In other words, it means performing a forward diffusion process. However, to achieve this using the unit's predicted noise, the process starts from the rendered image x0. It then goes through repeated denoising and noising steps according to the defined interval steps delta until reaching xt. The key here is that this process is solely about converting the rendered image into a noisy latent. This means that noise must be unconditioned without any text information included. First, x0 is fed into the unit to predict the noise at time step 0. This noise is then removed to generate the denoised image, that means pseudo-GT x hat. Second, the predicted noise at time step 0 is adjusted by multiplying it with the scheduling weight for the interval step delta, effectively scaling it to represent the noise for the 0 to delta interval. This adjusted noise is added to x hat, producing the noisy latent x delta at interval step delta. Then x delta is fed into the unit to predict the noise at time step delta. This noise is removed to generate the pseudo-GT x delta hat. Also, the predicted noise at time step delta is scaled by the scheduling weight for the next interval step 2 delta, representing the noise for the 0 to 2 delta interval. This adjusted noise is added to x delta hat, producing the noisy latent x2 delta at interval step 2 delta. By repeating this process, deterministic noise can be added in multiple steps, eventually producing the final noisy latent xt. When expanded into equations, it looks like this. Follow along with the video and take your time to review it step by step. The ultimate goal of DDIM denoising is to create multi-step pseudo-GT by removing noise from the noisy latent generated through DDIM inversion. In other words, it's a reverse denoising process. By following the noisy latent trajectory created during DDIM inversion in reverse, the process repeatedly alternates between denoising and denoising. denoising and noising until it reaches the multi-step pseudo-GT x tilde 0, x tilde 0. Even though the process is denoising, the final equation involves addition instead of subtraction. This is because when creating the denoised image, denoising is performed first, followed by noising to generate the multi-step pseudo-GT. Here the key point is that the pseudo-GT must correspond to the text prompt. Therefore, the predicted noise must include text information, meaning it should be text-conditioned noise. First, xt is fed into the unit to predict the noise at time step t. This noise is removed to create the denoised image, that means pseudo-GT x hat. Here the pseudo-GT x hat is different from the pseudo-GT in DDIM inversion, as the text conditioned predicted noise has been removed. Second, the predicted noise at time step t is scaled using the interval step scheduling weight to adjust it to represent the noise from 0 to t minus delta. This adjusted noise is then added to x hat, producing the multi-step pseudo-GT at interval step t minus delta. By repeating this process, text-conditioned noise can be applied in multiple steps, eventually producing the pseudo-GT x tilde 0. When expressed into equations, it looks like this. Following along with the video and take your time to review it step by step. Going back to the text-to-3D pipeline, the technique used to train 3D representations based on the pre-trained diffusion model is called SDS. The ISM, which stands for interval score matching, treats the noise predicted by a diffusion model as a score that shows how far the current result is from the target. Multi-step interval noise can be predicted through the DDIM inversion and DDIM denoising process. The ISM loss is then defined as the difference between these noise values. This can also be interpreted as the difference between images rather than noise, by expanding the equations in the same way as before. In this case, it represents the difference between the rendered image x0 and the pseudo-GT x tilde 0 obtained through the multi-step noising and denoising process. To wrap things up, the stochastic noise in the SDS noising process is replaced with deterministic noise in DDIM inversion. And ISM addresses the one-step limitations of SDS by performing noising and denoising across multiple interval steps along the DDIM diffusion trajectory. Here are more results of text-to-3D generation using ISM. You can see how it generates highly detailed and beautifully rendered objects even for complex designs. With this, it's possible to create entirely new 3D models that don't exist in the real world, like a white-haired Iron Man or a zombie Joker. While the traditional SDS method produced blurry and low-quality 3D models, LucidDreamer, which introduced ISM, generates highly detailed and high-quality 3D models. By changing the 3D representation and rendering method, both SDS and ISM can be applied, that NURF and 3DGS, 3D Gaussian splatting. It's clear that using ISM results in much more detailed 3D generation compared to SDS. This concludes the seminar on text-to-3D generation using SDS and ISM. The ISM strategy in LucidDreamer includes more detailed techniques and additional methods that weren't covered in this seminar. If you are interested, I encourage you to check out the paper for more information. If you need reference links for the images in this presentation, feel free to leave a comment. Thank you for taking the time to watching this seminar.